And on behalf of Nepal Polymer Institute, I, Santa Pokhrel, welcome you all to this 8th E-symposium on Innovation in Polymer and Material Science, IPMS, organized by Nepal Polymer Institute in technical collaboration with NREN, Nepal Research and Educational Network. This series of E-symposium is being organized to celebrate the 10th anniversary of Nepal Polymer Institute. Many globally recognized scientists have already delivered their beneficial lectures to our young researchers and scientists with the motive to spread knowledge about innovations in polymer and material science. Our guest for today's event is Professor Dr. Rameswar Adhikari, Founder President of Nepal Polymer Institute. Welcome you, sir. It is our privilege to Professor Dr. Steve Hordle, University of Nottingham, United Kingdom, as our keynote speaker. Welcome you, sir. We are delighted to have Professor Dr. Eva Malmström Johnson's KTH Royal Institute of Technology, Sweden, as our special guest. Welcome, ma'am. We have our previous keynote speakers as well, Patrick and Igor. Let me see, and all. Okay. Now we heartily welcome all the professors, faculties, guests, and participants present over here. I would like to request Dr. Rajesh Pandit, President of Nepal Polymer Institute, to deliver the welcome speech. Rajesh sir. Dr. Rajesh Pandit.
It seems Dr. Pandit has disappeared.
Okay, now due to some technical problem, Dr. Rajesh Pandit is not available over here. So now may I request Professor Dr. Rameswar Adhikari, Founder President of Nepal Polymer Institute, to share a few words. Please, sir.
Okay, thank you so much. This is a very wise idea. When Dr. Pandit is not here, then we can continue it this way. So thank you so much and very, very welcome to all our guests, all the faculty members who are joining here. Namaste, good morning, good afternoon. And yes, thank you so much, the members, the executives of Nepal Polymer Institute who are carrying this effort. And this has been very beneficial to our students, faculty members, and especially the graduate students. So I also would like to thank all of you who are joining over here. And a special thank is also to Nirajan Parajurejis, who is also over here listening to us, for your technical support, your support giving us the opportunity to utilize your Zoom platform. And this is really very, very big support. So we want to listen to our Steve, therefore, and our Eva, and I have a nice discussion. So I don't want to take much time. So I am very much looking forward to listen to you, Steve. Thank you so much. This is all I want to say.
Thank you. Thank you very much, Professor Dr. Rameswar Adhikari. Now I would like to call upon Dr. Shankar Prasad Khatiwada, Executive Member of Nepal Polymer Institute, to introduce our keynote speaker, Professor Dr. Steve Hordle, and our special guest, Professor Eva Johnson. Yes. Dr. Shankar, you are mute.
Thank you very much, Dr. Pokhrel. Very good afternoon Very good morning also. Now I would like to briefly introduce very renowned polymer scientist, Professor Dr. Stephen M. Hodel. He has completed PhD in 1989 in spectroscopy in liquefied noble gases. He has published 330 scientific papers in index journals, 12 patents, 58 years indexed, and 11,800 citation in Google Scholar. He has supervised a number of PhD students in the field of polymer research. Currently, Professor Hodel is working at University of Nottingham, UK as a professor. Likewise, I would like to introduce our next guest, a very renowned polymer scientist, Professor Dr. Eva Malmstrom Johnson. She has completed PhD in 1996 at KTH Royal Institute of Technology, Sweden. She did postdoc in 1996 at IBM Almaden Research Center, Stanford University, California. She came back to KTM Sweden again in 1997 and become a full professor in 2005. Currently, Professor Johnson is working at the Department of Fiber and Polymer Technology at KTM as a head of Division of Coating Technology and Director of Wellenberg Wood Science Center. Thank you.
Okay. Thank you, Dr. Sankar Prasad Khatioda, for short brief introduction about our keynote speaker and special guest. Now we have Dr. Rajesh Pandit, President of Nepal Polymer Institute. So I would like to, may I request Dr. Rajesh Pandit for the welcome speech.
Thank you, Dr. Santa. Sorry, I could not join in time. Sorry for delay. Okay, already Professor Dr. Rameshwar Adhikari sir already give the short speech to welcome all the distinguished guests. Likewise, I would like to welcome you all. Very good afternoon to all, respected keynote speaker, special guest and distinguished guest, and founder president of Nepal Polymer Institute and dear participant. It is our great pleasure that we are at the beginning of the event of E-symposium and Innovation in Polymer and Material Science series. I do not want to explain in the detail. Today we want to listen Professor Dr. Steve Hodel, his keynote speech on renewable polymers and clean synthetic approaches. He is an eminent scientist and professor in Nottingham University, UK. He is an expertise in clean chemistry, clean synthesis of polymers and supercritical fluids, mainly on supercritical carbon dioxide. I am very happy to welcome today keynote speaker, Professor Steve Hodel, and special guest, Professor Eva Malmstrom Johnson, KTH University, Sweden, in this program. Likewise, I would like to welcome you all, the participant and distinguished guests, and all the participants. Welcome you all. Thank you. And we have to listen the Professor Steve Hodel. Thank you.
Thank you, Dr. Rajesh Pandit. Now, may I request Professor Dr. Steve Hodel, our keynote speaker, to deliver his special lecture on renewable polymers and clean synthetic approaches. Please, Steve.
Thank you, Shanta. Thank you. So just checking that you can all hear me well, and I'll just go through the technicality of sharing my screen to make sure that can happen. And I hope that that will be working fine. So am I now showing my screen? Does that come through?
Yeah, we can see it.
You can see, and I'm hoping that that we can just make sure that I can do my pointing as well. So I shall turn on the pointer. Nope. One more time. There we go. We have a pointer as well, I hope. So good morning, everybody. So thank you. Namaste. And good afternoon, of course, to all of you in Nepal. So I'm delighted to have the chance to share with you some of our research from Nottingham. Of course, I have many, many examples of things that I could show you, but I've just chosen 3 different topics to give you an illustration of some of the things that we've been trying to do in Nottingham that are, I hope, illustrate what we want to achieve in terms of renewable polymers and in terms of green chemistry. Much of my work revolves around using supercritical fluids, so high pressure carbon dioxide. So I'll give a little bit of an introduction, and then I will show you some examples where we've applied them to polymer science. So here we have a view cell, and we work with high pressure carbon dioxide. So this window here, this is about 3 centimeters in diameter. And we're going to look inside of here as I push in some high pressure CO2, and I want to show you what a supercritical fluid looks like, because this is one of the areas that we have focused on in our research. And so here you can see what we get. We get some liquid CO2, and this is in equilibrium with gaseous CO2. And when we raise the temperature and raise the pressure, you can see the liquid is expanding, the gas is compressing, and eventually the densities of the two become the same. And at that point, the meniscus disappears. And this is a supercritical fluid. And then if I lower the temperature and pressure back down again, you can see we get the phase separation, and we go back to liquid CO2 and gaseous CO2. And what's exciting for us is that when we're at the critical point, we have a supercritical fluid, which is neither a liquid nor a gas. And so this is a very important aspect of the way that we describe the fluids. So here I put this into a more engineering or physics-based approach. This is a phase diagram. And you can see the 3 phases that you're all familiar with: solid, liquid, and vapor. And you'll be familiar with this kind of diagram. So if we go from a solid to a liquid, we have to increase the temperature. We move along where the red pointer is, and we'll pass over this line. We have to put in some extra energy, and this is the melting point. And then we would go from solid to liquid. And similarly down here, if we go from liquid, we have to go over this phase boundary here, and then we end up in gas, and that means we've passed over the boiling point. But there is a certain temperature and pressure up here, which is known as the critical point, where actually the distinction between liquid and gas completely breaks down, and we have a single fluid, a so-called supercritical fluid. And the way that I like to describe this is that a supercritical fluid is neither a liquid nor a gas, but a combination of both. And so we can dissolve things in our supercritical fluid, in CO2, just like you can dissolve them in a normal liquid. But also, like a gas, you have to hold it in a sealed environment. That's why I showed you that high pressure cell that we had at the beginning. So neither a liquid nor a gas, but a combination of both. Now, I'm not sure how many of you have come across supercritical fluids before, but they're actually very, very popular. So for any of us who drink decaffeinated coffee or decaffeinated tea, supercritical fluids are used to remove caffeine. They are used to improve the flavor of beer, to extract good flavorings from hops. There are all kinds of worldwide processes, and they touch us in many different ways. And actually, I was quite surprised to find that they appear in a lot of different areas. So for example, I'm sure that many of you will have heard about Harry Potter. And I did a little bit of research, and I noticed that the author, J.K. Rowling, even visited Nepal a few years ago to open up an orphanage, a hospital, and she came and met many people. And so these films and books are very popular. Now, when my kids were growing up, I read them the books every night. and we read one chapter per night for a few years. And this was part of our evening routine. And I'm not going to tell you the whole story, that will take too long. But there was in the books, there is this guy, the bad guy. He's called Professor Snape. We actually have a Professor Snape in chemical engineering in Nottingham, but he's not a bad guy. He's okay. Now, this guy meets with an unfortunate accident in the book. And J.K. Rowling writes in the book that something more than blood was leaking from Snape. It was neither a gas nor a liquid, and it gushed from his mouth. And I was reading this book to my children, and my youngest son, TJ, who was then aged about 5, he jumped out of bed. He said, Dad, it's a supercritical fluid. So you can see these fluids appear everywhere in everyday life. And I want to tell you just a little bit about some of the research that we've done using supercritical fluids. So I'm going to tell you about how we can use CO2 as a green solvent, about how we don't leave behind any solvent residues, about how CO2 is very inert. And in fact, many of our chemistry colleagues around the world are spending a lot of time at the moment trying to activate and to turn CO2 into useful molecules. And it's not easy because CO2 is so inert. There's also a lot of CO2 available from all of the activities that mankind has, and we can collect it and we can capture it and we could use it. So it's very cheap, very inexpensive. I'm just going to tell you about how we make some renewable polymers and we make some new nanomaterials using CO2 as a solvent, because it gives us some unique properties that perhaps wouldn't have happened otherwise. And I want to emphasize that in this work, we are not making any CO2. We are just using what's already out there and trying to find a good use for this material. So the first story I'll tell you came out of an international exchange. And I was at a conference and I met a colleague, Jonas Chibudi, who was from Ethiopia in Addis Ababa. And Jonas and I sat and had a coffee, and the Ethiopians know a lot about coffee. And we talked for a while, and we came up with an idea of a research project that we could carry out together whilst we were sat at a conference. This was in the old days when you actually physically went to a conference and met people and had coffee, okay? And we decided to do this, and we saw an opportunity to apply for some money, and we were able to get some money in late October 2017 to allow us to fulfill this research, which was really quite nice. So it just gave us some travel money and a little bit of consumables money. And as part of this, we got to travel, and I went to the chemistry department in Addis Ababa, and I took with me one of my PhD students, Mariana, who was from Portugal, and this is Jonas, who was showing me around. If you're interested, here I am wearing the football shirts of my favorite team. I'm not sure whether they would be a big name in Kathmandu or in Nepal, but I wanted to use my talk to educate you. So whenever you talk about football in England, you should always think about my team, and this is Rotherham United. So they play in the second league in the championship. And so what did we do? What was the science that we were carrying out? Well, we were looking at this material. So the ironweed is a plant that grows quite a lot. It's a weed that grows all over the eastern regions of Africa. And it produces these seeds called Vernonia seeds in a very big way. There's lots and lots of this material available. And it turns out that 48% of these seeds is a natural oil. And you can see this here. And we just thought it would be really useful if we could somehow turn these seeds and get this oil and produce something useful from this material. So we set out to do that. And we began this by looking carefully at the structures. And one of the major components of the oil is a triglyceride that contains vernolic acid. And by a process of hydrolysis, we can remove this vernolic acid and we can collect it as quite a good and clean material. So we went through this process and we showed that we could purify we could then use this material to create some new monomers and to make some new polymers. And I want to tell you this story. So the way that we extracted the oil was actually using supercritical fluids. So in just the same way that you can extract caffeine from coffee beans, we extracted the Vernonia oil from the Vernonia seeds. And we took it to a commercial operation in the UK, and we had 600 grams of seeds, and we put it into the apparatus and we pumped CO2 through, and it very effectively produced 240 grams of oil. And we could then take this oil, and it was very pure and very clean, and we could start to work with it. And in fact, CO2 is a very efficient way of doing this. It turns out that the extraction is much quicker than using the normal solvent in a SOx-less extraction. We use much lower temperatures, and it's actually quite selective for the Vernonia oil. The other oils that are present are not extracted very effectively using CO2. So I then turned to some organic chemistry, and I'm not a synthetic organic chemist. So I did this with my colleague Rob Stockman, who works just a few laboratories away. And Rob and I looked at these structures and thought about how we could turn them into a monomer. And what Rob showed was that we could take this really nice molecule, which actually does polymerize a little bit on its own, but not really effectively. And we did a little bit of simple chemistry on it, and we popped open this epoxide here, and we made a single alcohol group, and we made a diol. So you can see here we've got two different molecules in one quite easy step from vinolic acid. There are other things we've also tried to do to create diols like this and diacids, and they're still in progress, but these two worked very, very effectively. Now, if we take that and we look at it, what you can see is that we have now a molecule, and this is the monomer here. It's a liquid. And you can see here we have a carboxylic acid, and we have an alcohol. And many of you will know that that would allow us to do some chemistry. And actually, it polymerizes really quite well. We just used very standard tin octanoate, and we did the reaction in CO2. And we showed that we could get the polymer to form very easily in CO2. We used quite an elevated temperature to make this happen, but it worked very well. And here you can see an example of the polymers we made. When we ran the reaction for 3 hours, we got a low molecular weight material, which is quite runny. And when we did it for 6 hours, we got a much higher molecular weight material, and it showed us that we could get some kind of control. And with the second monomer, this time we have 2 alcohol groups on it. So if you're a polymer chemist, you'll realize that this could be useful for branching or cross-linking. And that's exactly what happens. So the monomer in this case is a solid. And what we did was we polymerized it in just the same way. And in this time, what we saw was the formation of some material that was just quite heavily cross-linked network. And this enabled us to produce some really quite new materials. Now, what you'll notice here also is there's these black round bits here, and these were just some molecular sieves that we added into the reaction to absorb the water from the condensation process. So this works reasonably well. And the other thing that we've done, which I didn't create a slide for here, is we showed that instead of using tin octanoate, we can actually use an enzyme, and we can do the polymerization at much lower temperatures using an enzyme and create very similar polymers. And the enzyme, natural catalyst, survives in CO2. So this is just 2 examples of degradable polymers that we can produce from natural resources, where we use CO2 to do the extraction and also to do the reaction solvent. And so we've got some really good news here, because you could take 1 kilogram of seeds, you could extract up to 400 grams of the oil, and then with a bit of chemistry, we can turn them into monomers, and we can end up with about 300 grams of polymer. So it seems quite a reasonable process. Now, I hope you notice here that the pictures of these materials are really quite nice, and they're artistic. Would you agree with me on that? They look quite nice pictures. And this was because Nottingham decided to have a year of culture. And during the time we were doing this work, they paired me up with a local artist. And this was Sarah Gaynor, who was a professional photographic artist. And at the end of this year, they asked Sarah and I to make a presentation at our local contemporary arts museum. And so we went together and Sarah presented her photographs and I stood up and talked about the work to the people of Nottingham. And it was a very nice occasion. It got me to mix with a lot of different people that I wouldn't normally mix with. I also was interviewed on local TV. So this is the BBC News. And this image was shown quite a lot around the UK and actually around the world. And when I was there, we had to wear a badge. So Sarah was an artist and she had a badge that said artist. And I had a badge that said scientist. And many of my friends and some fellow academics were quite amused to see me on the TV with a badge that said scientist. And I said, well, that's what I am. So it's quite a nice occasion. And here you can see some of the artwork that Sarah did. That was just quite a nice way of looking at the way that we did our science. Okay, so that's one story that I wanted to tell you about. The second one is a little bit different. And this is about looking at dispersion polymerization. How do we carry out the polymerization that makes reactions and makes new materials? And I want to show you how we use CO2 to make some unique structures that you just simply cannot access yet in conventional solvents. So dispersion polymerization means that we take an initiator, usually an azo initiator. We can then create two radicals like so, and then the radicals will go off and start to initiate the monomer. And you get to a point where the polymer chain becomes long enough that it no longer dissolves. And under normal conditions, it just precipitates. But you can avoid this precipitation if you add the right stabilizer or surfactant or detergent. And in CO2, these had been created. And my group made quite a lot of silicone materials. And Joe DeSimone in the USA started out by making some very nice fluorinated ones. And the surfactant simply sits on the surface of the growing polymer particle and prevents them from sticking together. And that means that the dispersion polymerization works very effectively. And at the end of a reaction, you can see that it has worked very effectively. So this is what we see. Here's one of our high pressure reaction autoclaves. And so you can see here we have a stirrer and we have the ability to inject in monomer and CO2 and to measure the temperature. And here's the polymer at the end of the reaction. So this is a dispersion polymerization carried out for a period of about 4 hours. But when we focus into this material using the electron microscope, this is what we see. So those particles that were stabilized by the detergent, you can see come out as particles and really quite nicely. And these have around about the diameter of 3 microns very effectively. And so this is stuff we were doing way back now, probably 20 years ago when we first began this work and we started to understand how to do dispersion polymerization. And as things moved on, I got to know more about the polymer community, and I began to learn about control polymerization and the fact that you could make copolymers and indeed block copolymers. And a block copolymer would be a length of polymer A, and then we add in monomer B, and we create a block copolymer. And it started to investigate whether we could get this to happen in CO2, which it can, but also inside the dispersion. And so we looked at using raft control polymerization, and we showed that we could get very nicely controlled particles of PMMA, polymethyl methacrylate, and the raft agent we were using worked very effectively to control the molecular weight. And also when we looked at the sample afterwards, you could tell the raft agent had worked because the sample has a yellow tinge, or in this case, a pink tinge that shows the raft agent is present. So this showed us we could use raft agents to build up molecular weight, to control molecular weight, and to allow us to make block copolymers. So we then moved on to trying to create some block copolymers. And this is quite interesting. So if you create block copolymers, you can make a run of A and then add monomer B. And what you try and do is choose A and B so that they hate each other. They don't want to mix. And so the polymer then will self-assemble and will form zones of B surrounded by zones of A. And this is well known and has been discovered for many, many years. And lots of polymer chemists and polymer engineers and polymer physicists have worked in this area. And it's well known how to control the different lengths of A and B and their different interactions to get these very different structures. But the vast majority of that work has been done in very thin films cast onto substrates. Very little has been done in terms of forming particles. So the question that we asked ourselves was, if we could get a dispersion polymerization to work and form particles, could we at the same time carry out this kind of block copolymer process? And if it worked, what would we see? Would we see some kind of phase separation inside the particles? And that's what we began to look at. And it worked beautifully. So here's the result of one of our reactions where we cut open one of those particles in the electron microscope. And what you're seeing now, it's like slicing through an apple. We've opened it up and you're seeing here zones of A, B, A, B, A, B, A, B, all the way through the particle. So this is very definitely a lamellar approach. And my PhD student at the time, James Jennings, explained this. He said, Steve, it's just like an onion. You get layers of A and B inside the material. And then if we changed the length of the two different blocks, we should be able to change the structure. So we were working with methyl methacrylate and vinyl pyridine, and we changed the lengths. And when we changed the lengths, we changed the structure. And we saw this. And this time, instead of lamella, we saw these spherical areas where we had zones of polyvinyl pyridine inside a sea of PMMA. And we decided this looked a bit more like a pomegranate. So we could change the structure. And you can see here that we're working with a particle that's of the order of 1 to 5 microns. And we have domain sizes here that are on the small nanometers, so around 20 to 50 nanometers. And we're engineering that by changing the block copolymer chemistry. So we got very excited about this and understanding how we could control it. And we showed that there's a whole range of different structures that we could create. So here you can see some lamellar ones. Here you can see some bicontinuous interpenetrating structures, some spherical ones with disorder, and some lamellar and some cylindrical versions. So all kinds of different structures that we could begin to create. And one of the questions that we asked is, can we watch this process? Could we actually follow the reaction as it happened? And for this, we decided that we needed to turn to doing some scattering measurements, and we used some small angle X-ray scattering. But a small angle X-ray scattering cell for working at such high pressures wasn't readily available. It didn't really exist. So we actually had to make one ourselves. And you can see it's based on the autoclave that I showed you earlier. But we've designed two special windows here so that we could push in the X-rays and then we could collect the scattered X-rays afterwards, analyze their energy, and tell us about the structure of the growing particles that we have in the medium. And this is the real vessel that we created. And this was an engineering challenge. Now you can see here the windows. So these windows have to allow X-rays to pass through. So they have to be very thin, but also they have to hold back a pressure of maybe 200 to 400 times atmospheric. So how do we do that? How do we get thin windows and hold back a high pressure? The original vessel I showed you right at the beginning of my talk had a sapphire window, but this is about 5 centimeters thick, and that just wouldn't pass X-rays. And it turns out that the best way of doing this is to create windows out of diamond. And diamond is strong enough. And we could also then have windows that were just a few millimeters thick and would be able to hold back the high pressure. And it worked beautifully. And the diamonds weren't that expensive. They're industrial grade diamonds, so they're not the ones that you might buy as jewelry. And it worked really well. And so we started to do some work, and we went to the beam line at the ESRF in Grenoble in France. And here you can see our vessel, and the X-rays are being pushed in and then collected into the collector here. And a whole group of people from my research group and from the ESRF were involved in doing these measurements. And we started to look at how in our polymerization, the scattering changed as the particles were formed. And here you can see what we saw. So if we have the PMMA block first, and then a small amount of the vinyl pyridine, initially we don't see anything. So for the first hour of the reaction, nothing changes. This is a featureless hump here. It doesn't show anything. Nothing is changing. There's no structure. But then things started to change. And as the polystyrene or polyvinyl pyridine, whichever one we're using, begins to grow in the zones, you can start to see some features appearing. And we began to move along a bit in time, and you could see the features appearing. And eventually, we could end up with some really quite interesting structures. And these we can then take and calculate. And so looking at the Q number that comes out of this, we were able to understand that these were showing us that the structure we were forming was cylindrical. And you can also, from this, you can calculate that the domain size that you are forming should be of the order of 25 nanometers. So when we took these materials and put them in the electron microscope, here's one of those particles that's been cut in half. And what you can see is some structure inside here. And if we analyze it, you can see that we have cylinders that have structure. I'm hearing a little bit of noise in the background. So we can see we have a structure here of around about 25 nanometers, which is exactly what we had predicted that we would get. And here you can see better that these have organized into a very definite hexagonal cylindrical array. So all of this is happening inside one of those microparticles. And we realized that we could do quite a lot of this. And the people working on this were Tom and Guping and Mohammed. And we spent quite a lot of time trying to understand how to do X-ray scattering and how to control what was happening. And also we realized that there were some very good opportunities here because we were creating structural hierarchy. We had very good control of microparticles. And within the microparticles, we had structures of nanometers where we could engineer them to certain sizes. And I talked again to some colleagues who were very interested in battery technology, and they told me that we should be able to take these materials and to template them to create some powders with these right kinds of structural hierarchy that could be useful in all kinds of applications. And battery technology, battery anodes and cathodes are just one of them. So we started to try and understand if this was feasible. And so how do we do that? Well, first of all, we will create the microparticles, as I've just shown you, with the structure inside of them. And here you can see one of the microparticles was the structure inside. And we've chosen now to use N-vinyl pyridine, 4-vinyl pyridine, as one of the monomers with methyl methacrylate. So this forms a zone where there's a lot of nitrogen groups present. And because of that, we can now add some titania and infuse this into the polymer particles. And this is work that's carried out by Tom Bennett and Ryan Larder, who's currently writing up his PhD thesis. And we made block copolymers with the idea of infusing titanium isopropoxide into the N-carrying blocks. And when this happens, the titania would like to stick into those areas. And what we can then do is we can heat it up and remove all of the polymer and just leave behind the titania. And the polymer should have acted as a template. So here you can see that we proved using Raman spectroscopy. So the bands of the CN are clear. And after we put in the titanium isopropoxide precursor, you can see a shift in the CN bands. So it shows us that the titanium goes into the zone where we want it to be. And then we remove the template by heating it up. And we do this by calcination. And we end up with a structure here that is a match templated from the original polymer. But there's now very little carbon, no carbon present at all. It's just all TiO2. And here you can see the SEM, and you can see that we've retained that spherical structure. These are still microparticles. And when we look in very closely, you can see the structure here. And then if we started to actually cut one open, you can see that the, the sacs shows us that we still have the same kinds of structures present. The particles have shrunk in size a little bit because they're now no longer made of polymer, they're made of titania, but they have retained their structure. And we did this not only for titania, but also for this lithium iron phosphate, which is another one that is a material that could be used in many forms of the battery capability. And we confirmed their composition and structure by using some EDAX so looking at the X-rays that are kicked out in electron microscopy, and we can show that we very definitely have the anatase structure of titanium dioxide. And here you can see this. And similarly for the lithium iron phosphate, we've got very similar behavior, and we can show that we're getting the right olivine type structure when we look at the crystal structure of these materials. So we've designed our polymer materials to enable us to template into some metal oxide materials. And looking very carefully at them, you can see here that we get some really nice crystallographic structures of the metal oxides, and we can see very clearly in the X-ray, in the electron microscopy here, we can see very clearly the phase boundaries of the crystal structures. And we also found there's a little bit of carbon coating left behind that again should be useful for the technologies going forward. So if we were to create this for battery materials, we have to do it on some form of scale as well. So we've spent a little bit of time trying to scale this up, and we can make gram quantities of our polymer materials, and then we can convert them through into the metal oxides, and this works really quite well. So scaling up would also be important. We have to show that we can do it, and we can also go even further because we've now developed a high pressure supercritical fluid vessel that has a 1 liter scale. So we could create up to 250 grams of polymer in each reaction. So this will enable us to begin to scale up. So I think this is quite important. Now, the battery testing and the ability for them to work as anodes is something that's still going on, and we're working with a group in Switzerland, and that's ongoing, but it's showing some promise. And I hope that you might invite me back sometime and I could tell you a little bit more about how that's coming together. But the important thing is we've used CO2 to create these unique structures. So what next? Well, one thing that we looked at was these structures here. And one of my colleagues, Gu Ping, understood that we have these domains of vinyl pyridine, and that they can be quite good at absorbing solvents as well. And so she decided to play with them. And we ended up creating these things, which we called holy balls. And you can see that these microparticles have now swollen a little bit and are very porous. And the pore sizes here actually correspond very well to the domain sizes of the vinyl pyridine that was inside the structure. Now, how has this happened? So we had to look at it very carefully. And what we understood was that if we added ethanol, the ethanol would preferentially go into the vinyl pyridine zone, and it would swell in the vinyl pyridine zone. And then if we added a little bit of hexane, the hexane will cause this to collapse. It would force out the ethanol because they don't like each other. And this hexane removal and forcing out of the ethanol caused the porosity to appear. And so we did a whole series of work that showed that we could control the porosity of just the polymer materials. And here you can see we've used some different block lengths to control the pore sizes and different block ratios to control the pore sizes. And we're just beginning to build up now our understanding of how we can control these pore sizes to create some very finely controlled porosity inside these microparticulate materials. And one of the things that we did here was we've got a very good electron microscopy suite in Nottingham, and started working very closely with the electron microscopists, and they showed us some really fancy techniques. And I'd never heard of slice and tilt, but it's a sort of tomography that you can carry out in TEM, transmission electron microscopy. And I'm going to show you a little movie that we built up of two of these particles. So here are these particles inside the electron microscope, and you can see that they've used the electron microscope to pan around the structure and to prove to you that these very definitely are porous all the way through. So it's not just on the surface, and you can image this as you rotate these particles around. And I'm still amazed by electron microscopy and the ability to be able to manipulate these things that are just a couple of microns in size and to move them around. But here you can see the very nice structural porosity that's in there. Okay, so what Ryan has been doing now in his PhD, he's been extending this, and we're now working with tri-block materials, and we've taken PMMA and then added styrene and then added vinyl pyridine to create a tri-block material. And we've followed this process, and Ryan has shown that when you have the di-block material, it's a lamellar separation. And here's the electron microscopy image that proves it. And then when you add in the third block and grow it onto that, the vinyl pyridine only has one place to go, and it has to go into the polymethyl methacrylate, which it also doesn't like, and it phase separates again. And we get this sort of spherical arrangement inside of the lamella. And when we look inside the particle, we'll see some really quite unique structures. And it's well known that TER polymers, TER block polymers, show more structural variation, and we wanted to try and do this. And Ryan has shown that we can actually now get to looking at these TER block copolymers. And again, he's converted these into some inorganic oxides. So here we've gone from the tri-block polymer to putting in the titania and then annealing it to create quite an interesting structure. And it turns out that the isopropyl oxide doesn't penetrate all the way to the middle. It just penetrates into the outer layer here. And so when we do the annealing, we end up with an outer layer of a very porous titanium material, and inside the particle is completely hollow. There's nothing present. And so we've looked very carefully at the surface area of these materials, and it turns out to be reasonably good. And what Ryan has showed, working with some collaborators in Brazil, is that this titanium material acts as a very nice porous-based catalyst that can allow us to do photocatalysis and convert methanol into hydrogen. And we've begun to show this. Now, the results we've got are very preliminary. People have converted methanol to hydrogen before using photocatalysis. But what we've begun to show is that we can do this very effectively, and that our tri-blocks are much better than the di-blocks, and we get much better hydrogen evolution. So maybe we're on the way to making some structured catalytic materials here that could be of interest going forwards. So what I've done then for the first two parts of the talk, I've shown you a little bit about how CO2 is a green solvent and it can be useful. I've shown you about making some molecules from renewable materials from nature. We've also done this not only with ironweed, but we've done it with terpenes. We've done some stuff with tree bark and with some sugars. We've made a whole range of surfactants and polymers. And then I've also shown you some new nanomaterials where we've used the unique properties of CO2 to construct very structurally ordered microparticles with nano domains that we can control. And we've used those in templating. And it turns out that so far you cannot do this in a conventional solvent. So CO2 just has the right level of low viscosity and high diffusivity to allow this to happen. Now, for the last 5 minutes of the talk, I'm going to just tell you about something else on a bigger scale. So not a nanomaterial, but I'm going to tell you about some experiments we've been doing at Nottingham that look at the whole building. So this is our chemistry department, and it was built in 1962. And so quite old technology now. And one of our challenges in society is we have to reduce energy costs. And lab environments are very, very inefficient. So if you think about all the fume cupboards and the heating and the things that we do in our labs, we use a lot of energy. We also use a lot of water in cooling in our buildings for our experiments and for everything that we do. And at Nottingham, we use more energy than the university medical school, which is near to us. So the chemists use a hell of a lot of energy. And we also use more water than the university swimming pool. So it's not a very efficient way of doing chemistry. And heard from my talk, I'm priding our research on being green chemistry, and many of my colleagues are very concerned about the environment. So we set out a few years ago to do an experiment, and we were working with the company GlaxoSmithKline, and they are interested in creating new buildings that will have less of an impact on the world. And they want to be able to put up new research facilities all over the world where they have zero impact on the environment. And they chose Nottingham to work with us to see if we could make a GSK carbon neutral laboratory. Can we design a building that doesn't have an impact on society, but also one in which we can do research chemistry? And this was a challenge. So from a building perspective, this is quite interesting. So we came up with the idea that we would site this new building in another part of our campus. We'd have photovoltaic cells to collect sunlight, and we'd have all kinds of other things that I'll tell you about that would help us to make it fantastically energy efficient. And this is what we set out to make. Now, when you're building a new building, there are some things you have to consider. And when you create a building, you have to put in the foundations and the substructure. So that will always have a carbon penalty. So there's a lot of energy that goes into creating the foundations. And there's also a lot of energy that goes into creating all of the services and allowing you to put in windows and allowing you to put in photovoltaic cells and things. So somehow you have to think about how you might pay back that energy, those carbon tons. You have to pay them back, and you have to get them back quickly. So we reasoned that the best way of doing that would be to look at the superstructure of the building and to build it out of wood, because wood is obviously coming from trees. And our colleague Eva Malmström lives in Sweden. She'll tell us a lot more about trees, I'm sure. And if we could build the building out of wood, then this would enable us to use up a lot of CO2, to capture a lot of CO2 and to pay back the cost of doing the other things. So this is a design that we had. And we also designed in these chimneys here, which you can see are slanted back. And the building itself is shaped like an aeroplane wing, so that when the wind blows, the wind comes in, it accelerates, and it helps these chimneys here to draw air from inside and draw it out, and to help to power the fume cupboards. So to lower the energy that's required to do the extraction in the building. So it's wood, and it's designed to help to cut down energy. So this was the interesting thing that we looked at. And here was the ceremony when they began to do it. And they started this at the end of 2013. And here you can see somebody from GSK and our Vice Chancellor, and they even commissioned some wooden spades to do the first digging to show that they were going to be completely green. So we use wooden spades. And the building began. And here you can see the building is beginning to come up. 3 of the chimneys are in place, and everything is coming ready. The wooden substructure is just about ready. And this is how it looked in September of 2014. And everything was coming along very well. But then there was disaster. And we got lots of phone calls, and there was a fire. The building has set on fire. The security companies had put up some lights to help them walk around. One of the lights got hot, and it triggered off a fire. And this was the biggest fire in the Nottinghamshire area for more than a century. And suddenly on national TV, I tuned in and I saw our department was the headline news. It was burning down. So very fortunately, we weren't in the building. If I just go back, you can see it's not completed. Nobody was in it. There was no equipment in it. There was no chemistry. There were no people. But it wasn't a great situation. And the following morning, you can see here from this camera image that it's completely destroyed. So this was a big disaster. But our university and GSK were convinced that this experiment was the right thing to do, and they wanted to help it to happen. So we began again, and now the building is open. So here you can see the completed building. It was opened just a couple of years ago, and you can see here the chimneys and the entrance to the building. And here you can see some of the thermal lagging. We've actually grown grass on the roof to help to do keep heat in. And the building works really well. Here you can see the shape of it with the aeroplane wing I described. And here you can see the chimneys that help us to extract, and it's very efficient. Inside, it's all very woody, lots of wood. And you can see here some of the areas where we can meet. There was a grand opening party, and we even have now a piano in there. And Daniel is one of our PhD students who's a very accomplished professional musician. And he was playing at the opening ceremony. And inside the laboratories, all configurable. We can move things around. So every single piece of equipment is low energy. We can move the apparatus around and reconfigure the laboratories. The fume cupboards are very efficient, very low energy. And the building is running, and it's running very well. But what about the fire, I hear you ask? Were you stupid to build a chemistry building out of wood? Well, all of the architects beforehand told us that this was not a problem, that wood was actually not as flammable as people would believe. And some interesting data came out of the fire. So it showed that at this point, in the middle of the fire, the substructure was still standing. And this was still standing many hours after a conventional, normal concrete building would have completely collapsed. And the fire engineers were absolutely amazed. And the reason is because these big wooden struts actually form a charcoal intumescent barrier around them that keeps them stable. And so this was much more stable than anybody would have expected it to be. So this was very positive news. And then also, in the middle of the fire, I wanted to show you how very well the chimneys were extracting out the heat. And you could see that they very effectively were pulling the vented materials out. So the design had worked very effectively. Now, I wouldn't say that this was a control experiment. We didn't do this deliberately, but it did show us that, that the building could function very, very effectively. And so now we have our new building. It's up and running. We've been working in it for now two and a half years. It's designed to pay back its carbon credits over 25 years. That was the original design. Things are going so well that it will actually pay back the carbon credits in 16 years. So it will be carbon neutral in 16 years. Of course, to add on to that, we have to put on another 8 years because of the loss of the first building, but we won't talk about that. But we've shown the principles that this could work very, very well. So it doesn't occupy everybody, but there's a large number of people in there, over 100 researchers, instrument rooms, teaching laboratory, and a space for outreach activities. So I wanted to give you a bit of information about what we've been doing on the wider scale of green chemistry. But just to go back to research, I don't do any of the research. I don't go into labs anymore. I have some really valuable people. And in these modern times, this is my research group, and we all meet on Zoom. And I particularly want to thank Vincenzo, who's running the laboratory on a day-to-day basis and has been a fantastic source of ideas. So Vincenzo Teresco. There's Ryan here, whose work I spoke about a little bit. And there's Cartini here, and some of her work is moving us towards some quite interesting structures that maybe I'll be able to tell you about next time. And many other of these guys here have got really interesting projects that I haven't been able to talk about today, but I just love working with them. And this is part of the fun of being a scientist. So I'd just like to say thank you for listening to me. Over to you.
Thank you.
Thank you, Professor Steve, for the wonderful talk. Can I hear?
Yes.
Okay. Now, please, okay. Now I would like to request our special guest, Professor Dr. Eva Armstrong Johnson, to share her thoughts and ideas on the topic discussed by the speaker, Professor Dr. Steve Hurdle. Dr. Eva, please.
Thank you very much. I would like to start by complimenting you, Steve, for a beautiful lecture and also bringing in a lot of artistic presentation and a lot of artistic science into the work. It's absolutely beautiful. And I would like to start where you ended, by this magnificent building. Being able to, first of all, persuade the university to construct a sustainably designed chemistry building. I think that's a key for the future. And the beauty of sticking to wood in the main construction is absolutely fantastic. So I hope that this building can really become a role model for newly developing chemistry departments all around the world. Congratulations to a beautiful work on that. And then coming back to the beautiful presentation, the scientific presentation that you gave, I want to thank you for shining so much light on the supercritical carbon dioxide and what potential that a medium carries, both with terms of material synthesis, but also as a very benign solvent. The first topic that you covered, where you described your collaboration with a colleague in Addis Ababa on Vernonia seeds, I think it's incredibly timely in identifying a renewable resource that contains a compound in decent amounts is very timely. And then that you show that by clever chemistry, you could actually, first of all, isolate vernolic acid, and then further modify vernolic acid to create building blocks into which you could make materials. And also the fact that you were able to identify a building block that was pretty abundant make this a very viable and also, again, a very interesting pathway in finding materials for a more sustainable future. Again, I will have to compliment the Nottingham people for making this nice artistic show, also putting you on the BBC television. I think it's a beautiful way of promoting science in a very good way and making it more available to the community, Steve. So again, I think it really tells that Nottingham is proactive and progressive in this matter. And also telling to the wider community that the idea of designing material in this manner is very important for us to find out a new pathway to a more sustainable lifestyle. And then your second part with regards to dispersion polymerization, I think you showed that by very beautifully, again, by clever chemistry, designing hierarchical structures, first of all made of polymers, but then that you could transfer the hierarchical structures into those metal oxides like titanium dioxide, for instance. It's also a very nice way in transforming polymer chemistry, building nanostructure materials that then can play a big effort and importance for further applications. So really amazing and beautiful work. And this also your proof of engineering skills in designing your in situ SAX analysis setup is absolutely fantastic. And I think that also should inspire chemists all around the world to take the next step and not be scared off by severe challenges in managing to figure out more. I think in my mind, I think your presentation tells us many things. We need to develop sustainable chemistry in clever ways that you've shown a beautiful proofs of. And we need to design materials in a clever way so that we can actually obtain functional materials out of those hierarchical structures that you accurately now can control. And in the last point, I think you truly demonstrate that you're a scientist because you wanted to bring forward your ideas from chemistry into your mega project in making this building in a sustainable manner. So altogether, I think your presentation, Steve, is a beautiful example on how you can bring beautiful chemistry into sustainable materials and also bring functionalities in a completely new way. So thank you very much for an incredibly inspiring lecture, and I'm looking forward to learn more in the future. Thank you so much.
Thank you, Dr. Eva, for your views about today's lecture of Dr. Steve Odell. Now we proceed towards the discussion round. The floor is open for all the participants. If you have any queries, you can ask as well, or you can drop the queries in the chat box as well. Any of you, please?
Okay. May I put some questions, Santa? I'm raising my hand.
Okay, yeah.
Hello, Ram.
Yeah, hello.
Yes.
So thank you so much. Very, very nice lecture. Well, I'm very, very happy to learn about your new things about tri-block polymers. So long ago, these kind of materials were introduced by Raymond Stadler. It was the time when I was doing my PhD, long ago. So you introduced more improvement, more innovations in this kind of materials today. So I'm interested to know how you, because you explained, but I did not get it. How do you introduce titanium nanoparticles into di-block and tri-block copolymers? I did not get it correctly. This is my first question. So for example, if I take any kind of amphiphilic block copolymers, in which one of the page is hydrophilic, so please suggest how I can make it to accommodate any kind of nanoparticles. My first question. And the second is, this is my last question also. So you told that carbon dioxide is very cheap, it is very easy to make and so on, but for me it is very expensive. Because I don't know, and very, very difficult. So if it is so easy and so not so expensive, you have very nice young students, they would be perhaps interested to come to our country together with you. Please come one day with some of your students and teach us in our chemistry department. How can we make it? Because I have in mind different kind of oils, that are useless otherwise, but we are thinking of making some soap out of it. Maybe we can make some block copolymers out of these Himalayan oils. So, and I have the last question I forgot before. So you started with 1 kilogram of oil and you got 0.3 kilogram, 300 grams for making the polymers. 300 grams. And what did you do with 700 grams? What happened with that stuff? So thank you. So thank you so much. I want to listen to you first.
Okay, I just tried to make a list of the questions so I don't forget anything. So, so first of all, how do we put in the titanium dioxide? This comes in the form of a precursor, titanium isopropoxide. And the titanium isopropoxide is very well soluble in conventional solvents like ethanol. And so all we do is we take those particles that we made, a polymer, and we put them into an ethanol solution. And we stir them around for a little while. And the titanium isopropoxide is carried by the ethanol into the polymer, and it absorbs inside the regions where the vinyl pyridine is. So then we dry the particles and remove the ethanol, and then we take them and we put them in the oven and we calcine them. And when you do the calcination, the isopropoxide ligands fall off and come away as isopropanol, and the titanium dioxide forms in the shape of the template. So we don't put in nanoparticles of titanium, we put in a liquid form, and then it forms titanium dioxide in situ and follows the template. And that's a very standard way of making a metal oxide precursor polymer chemists have been doing that for many, many years. So this is all done by conventional routes. So the CO2 part is the part that we use before that to create the unique structures. And that's a really where we have to use CO2 because we can't get those structures to form using conventional methods, not in the microparticulate route. You asked me about could you use CO2? Well, yeah, this is one of the things that we need to do. And in fact, on this call today, there's some of my research group have come along, and some of them are undergraduate students or master's students who we taught to use CO2 in just a few weeks. And they've begun to do an experiment. So we designed the equipment to be usable, to be safe. Clearly, it costs more than glassware. So it is more expensive. And this is one of the worries for the future. How can we persuade people to do more green chemistry, more sustainable chemistry? And we have to show the benefits. And so my hope is that we can demonstrate some of the benefits to our science and show that it would be worth the effort to understand how to do the high pressures at the bigger scale, to create new materials or to save energy on the planet. Those are the things that will drive it forward. Nobody is going to do anything in CO2 just because I say it's greener. This doesn't get anybody. It's not going to excite anybody. There has to be a real benefit. So we have to show an energy saving, or we have to show a new product that you couldn't make in a normal way. But CO2 has been scaled up to the very big scale. There are plants in Germany and in France that work with 25,000 litres of CO2 to carry out processes that are around extraction. So very large scale apparatus. And so I think that the future could be there, but we have to demonstrate to people why they should invest effort into it. And in terms of us coming and working with you, I'd be delighted. I've often been, we went to Addis Ababa, we've been to other places. Some of our equipment is portable and we can bring it along and we can assemble it. And I think it could be possible. It would be a nice thing to do. So this is certainly the way to educate and to spread our methods and to show that it would be possible. And I'd also be delighted to host any of your students who could possibly come to Nottingham when the world becomes normal again. And we often host people to come and do experiments with us. And now I remember, I'm showing you my good memory now. You had another question and you said that we extracted a kilogram and we used 300 grams to make monomer. What happened to the extra 700 grams? Well, that wasn't just the oil. It was a kilogram of seeds. So inside it, there is oil, and we extracted almost all the oil. But the 700 grams left behind is actually the seed material, the solid material. And in the past, well, we know that you can't feed this to animals because the oil is toxic to the animals, and so it makes them very ill. But we worked with the colleagues in Ethiopia, and what they feel is that when we've extracted the oil, the 700 grams of seed that's left behind is now actually good protein-based material that they can feed to the animals without poisoning them because the oil is gone. So this is another experiment, and I'm not going to do this experiment because I'm not an animal expert, but in principle, that 600 or 700 grams of waste seed material could be used again and maybe form animal feed or some other potential useful material. So Ram, I hope I answered your questions.
Okay, now Marina, do you have query? Do you have any question? Jan Marina?
Yes, thank you, Steve, for a very beautiful lecture. Especially the control of the hierarchy of the particles was really great. So I have just few comments maybe about also the first part about the extraction of the natural oil from the seeds. My idea, what I was thinking when you show the comparison with the conventional extraction solvent, the time and the temperature which has to be used. I think it's also maybe the role of the high pressure for the supercritical carbon oxide that makes the extraction more efficient, and maybe that should be more fairly compared maybe also with high pressure solvent extraction? Because I think for extraction the role is about the similarity in the polarity, maybe that's the key, and it will very much depend what you extract, of course. So for these products, maybe CO2 is beneficial, like for caffeine or something like that, but maybe also the efficiency comes from the high pressure. And at the same point, on my opinion, there comes also the energy demand, because it's not only the temperature is lower, but the pressure is higher. So that's also energy demanding. Yeah. So maybe to make the comparison more fair, maybe that should be also.
I can answer that, but
yeah. So maybe if I can answer the second question later, maybe we can just go.
Yeah, sure. Go ahead.
Okay, and the second question about this oil and the chemistry you did. My question is about if you can comment on the purity of the hydroxy acid which you were able to obtain, because what you shown, the viscosity of the polymer products, it's still liquid. Yeah, so it seems more like oligomeric product. So if you can comment on the degree of polymerization of these products, if it is which determines the mechanical properties. Yeah. Okay.
Sure, Jan. So the second question, yes, I showed you two examples, and there are two polymers there. I didn't show any GPC data, which for the polymer chemistry we should show, of course. But the molecular, the first one was very much an oligomer, so probably it's something of the order of 10 units. DP was about 10 or 15, so just an oligomer. But that would be fine if we wanted to create a surfactant of some description. That would give us the right kind of level. And the second sample, which I showed you, was much higher molecular weight. It's probably of the order of 50 dp, and was getting towards what you and I would consider a proper macromolecule. So again, I need to go back and refine these, and we're just writing up the paper now, ready for publication. So we have to have all that ready. So it's not been published yet. But I think we're making real polymers. They're not just small oligomers and oils. And then to your first point about pressure and about energy, that's a really, really good point. You're absolutely right. We have to show these things are not only economically viable, but also realistic. So to the point about compression costs, you said to me that we have to compress the CO2 and this costs energy. It does, but it actually costs a lot less than it does to heat up to 100 degrees C. So with lots of different areas here, the compression cost for CO2 is actually quite small. So if I compare, and we did this real calculation we did, if we were to look at doing a dispersion polymerization in water to create some microparticles and compare that to doing a dispersion polymerization in CO2, what would be the advantage? Well, it turns out that the compression cost to get a ton of CO2 into the supercritical state is 2 orders of magnitude less than the energy you would need to boil off the water and dry the particles that you created if you use water as a solvent. So we're saving because the energy cost in getting rid of waste solvent and heating up and boiling off is really very high. The compression cost for pushing CO2 and squeezing it is actually quite low. Mm-hmm. So we've done this sort of relatively high scale calculation and shown that it's a viable opportunity that could take us forward. So that's one of the questions that a company will ask me when we first talk to them. And then you mentioned about pressure itself. Well, I don't think there's anything to gain by, if you take dichloromethane and pressurize it, I don't think it gives you any extra extraction ability, because you're really your extraction is really concerned by how easily the molecules can penetrate in and how good a solvent they are. And this is where CO2 has a real advantage, because actually the pressure, of course, enables us to get the density, but also we have very low diffusivity and we have no surface tension in supercritical CO2. So it's very effective at penetrating really quickly into any medium. And this is where there's a big attraction for using CO2. So I can't give you figures on this, but I do know the principles behind why that pressure equation should work for us.
Okay, thank you very much. Great.
Thank you, Jan.
Okay, thank you. Now, I think there is a question from Ambadat Panta. He is asking about that, is there any polymer in which atomic hydrogen diffusion is high and easily emit from surface of the polymer?
So atomic hydrogen diffusion. I have to say I don't know much about atomic hydrogen, so I've never used atomic hydrogen. But what I can say is that the reason why we would use CO2 is because when we play with polymers, the CO2 is terrible at dissolving polymers, but it's very good at penetrating polymers. And so it penetrates in between all the chains, gets really effectively inside because of the high diffusivity and low surface tension and low viscosity, and we can carry molecules in. So potentially if you have a precursor that can deliver you atomic hydrogen, maybe we could use CO2 to carry that into the polymer, and then we could switch it on and you could have that. But I don't know the background to why you might want to use atomic hydrogen. So I have to profess on that. Ram, you do
perhaps, yeah, I don't have the answer too, but perhaps Dr. Panta, konnichiwa, Dr. Panta. How are you?
Yes, fine.
Yeah,
sir.
Yeah. Perhaps you can add some points and you can elaborate your thought why you want atomic hydrogen get into this polymer. Perhaps okay, you can explain yourself. Thank you.
Yeah, actually, may I actually speak? Just one minute. Okay. Yeah, I am doing some material science. I mean, searching new material, functional material for hydrogen energy or hydrogen, how to say, storage material. And what we are doing is searching material in which diffusion is also high, and that can emit from surface, I mean, easily release from surface of polymer. So I think this is the very best place because here are many polymer scientists. So I put this question. If this is out of this talk, please forget this one. This is my what question and what I want to do. Yeah. Thank you for our attending me this one, especially Rameshwar sir. And it is very wonderful talk. Thank you, Professor Steve. Yeah.
Thank you. Thank you for your question.
It's essentially not only talk, but a very inspiring story also, I feel, from this talk. Thank you very much.
Thank you.
Any queries from participants? Any question from young researchers, young scientists?
Every question is welcome. I'm very happy for you to ask me a question. Please do.
Yeah, please.
The young scientists are the future of the world. They should have all the questions.
Yeah, they have many questions in their mind, but they don't want to explore it. Just, I think no more questions, no more queries.
Yeah, I do not have question, but I want to make a comment for my student who is also listening here. Sonam Tamang, you are here?
Yes, yes.
Our graduate student, Sonam. Yeah, Sonam is working with black polymers.
All right.
So
okay.
she is trying to make transparent blends of epoxy resin with black polymers.
No, I am not working on black copolymers. I'm working on pharmaceutical polymers.
Okay. But you could do that. Shankar is working on this. So, but you could take some black polymers and also black polymer with some nanoparticles into it, so that you could increase your increase the toughness of your polymer.
This Shankar will do.
Yeah. In our group, Steve, some of our students are working with epoxy resin, and they are mixing very valuable black polymers so that the epoxy resin's toughness can be increased.
I think Dr. Rajesh Pandit and Shankar Khatiwala
also, yeah. Okay, thank you.
Okay, I think now there is no more question. One more, Okay, here is one question from Eva. What surface areas can be achieved from the calcinated titanium oxide nanoparticle?
So we have surface areas of around about 150 to 200 meters squared per gram. So those are reasonable. They're not exciting surface areas. So people working in catalysts or in MOFs or these other areas, they'll be looking at thousands of meters squared per gram. So we're a long way from that. But these are good enough to act as useful materials.
Thank you.
Okay, thank you, Professor Steve, and all of you. Now, this is the end of the technical session. Now, I would like to request Dr. Jyoti Giri, Treasurer of Nepal Polymer Institute, to facilitate Professor Dr. Steve and Dr. Eva with the virtual certificate. Dr. Jyoti, please. Will you read?
Thank you very much.
Jyoti, will you read the certificate or just? Please, your mic is mute. You are mute.
I think now it's fine.
It's fine. We can hear you.
Yes.
No. Okay, thank you so much. It is my pleasure to read out this appreciation letter for Professor Steve and Eva. So it's a E-symposium Innovation in Polymers and Material Science, IPMS, letter of appreciation. This letter is presented to Professor Dr. Eva Malmstrom Johnson for contribution as a special guest on renewable polymers and clean synthetic approaches in 8th E-symposium, February 19th, 2021, organized by Nepal Polymer Institute, NPI, Dr. Rajesh Pandit, President, Nepal Polymer Institute.
Thank you very much.
This is for the Eva. And next is for our special guest. This letter is, oh, sorry, same came again. What's?
No, same.
Oh my God. What is the problem? I guess.
Oh, please don't worry.
Sometimes it is a kind of copy-paste effect.
Please don't worry.
They both are same. They both are same, but okay.
No problem. Just read about
yeah.
And,
yes. I just would omit it one and.
Oh, please don't worry.
Yeah. I just read this certificate. Letter of appreciation. This letter is presented to Professor Dr. Steve Hoddle for contributing as a keynote lectures on renewable polymers and clean synthetic approaches in 8th E-symposium, February 19th, 2021, organized by Nepal Polymer Institute, NPI, Dr. Rajesh Pandit, President, Nepal Polymer Institute. This would be the correct letter of appreciation, but there's some effect of copy-paste, I guess so. So I apologize on behalf of organizing committee, Professor Steve. Corrected won't be sent to your email account.
Please don't worry. And Eva and I are often confused because we have very similar hair.
I have the ponytail now.
Okay, thank you, Dr. Jyoti Giri. Now we are coming to the end of this 8th E-symposium. I would like to extend our sincere thanks to our guest, Professor Dr. Ramesar Adhikari, founder president of Nepal Polymer Institute, for his continuous support, suggestions, motivations, and guidance in each and every step. We are also thankful to our speakers and speaker Steve. Special thanks goes to, and also for special thanks to our special guest, Dr. Eva, uh, for enlightening our program with their valuable talk. Okay. Now, I would like to thank our previous speakers as well, who, Professor Dr. Patrick, who already lived, and Professor Dr. Igor Lesik, as well as he also lived us. And we have also faculties from the different institutes, Dr. Jen Marina and Professor and Dr. Arvind Pathak and Santu Srestha from the different colleges. And we are highly acknowledge Nirajan Parazuli from Nepal Research and Educational Network, NREN, for their technical collaboration with us. Thanks goes to all the executive members as well of the Nepal Polymer Institute, Dr. Rajesh Pandit, Dr. Sarmila Pradhan, Dr. Jyoti Giri, Dr. Shankar Prasad Khatiwada, and Kumar Khadka, sir. Special thanks goes to all the participants for joining us from Nepal as well as from abroad as well. After this, now moving towards the end of this session. So before this end of the session, now I would like to all of you put on your camera on and for the group photo. And after group photo, we will have Dr. Rajesh Pandit for his concluding remarks of today's program. So please, all of you, open your camera. So we will take the. Please, all of you smile.
So we don't see it yet.
Yeah.
So you want everybody to put on their camera?
Next page, I have. Yeah, all of you, open your camera, please.
This time we all are going live on Facebook page of Institute, as well as with the NREN page and many other Facebook ID also.
So we should smile.
Okay.
So
now,
hopefully
Dr.
we will get some electronic tea or electronic coffee.
Yeah. Okay. Now, Dr. Rajesh Pandit, please put on your concluding remarks and close this session.
Okay. Thank you, Dr. Santa Pokre. Once again, namaste and very good afternoon. We are at the end of the program. The E-symposium on IPMS is going to be very fruitful. That's why the lectures are also moving toward the specific topic with current emerging research. And today we get the knowledge on superfluids, polymerization with tin octanate in supercooled carbon dioxide, dispersion of polymerization in CO2, microscopic structure of PMMA, and supercooled carbon dioxide in 1 liter, blocopolymer, nanoscales, and so on. Thank you, Professor Steve Hodel, for your wonderful and very informative lecture. And we can get the specific knowledge in supercooled carbon dioxide in your lecture. Thank you very much. Likewise, I would like to thank Professor Eva Malmstrom-Johnson for your valuable time and share your expertise with us and made the program fruitful. Likewise, I would like to thank Dr. Santa Pokhrel for nice hosting the program, and similarly, Mr. Nirajan Parajuli, Nepal Research and Education Network, NREN, for technical hosting, and as well as technical collaboration for the to conduct this program. Likewise, I would like to thank you all. I do not want to repeat once again. I would like to thank all the participants from the abroad, from Germany, Czech Republic, and the US. Also, I have seen Japan. Also, thank you, and also the participant from the country side. Your regular participation make us more excited and continues to conduct the series. Thank you your support and active participation. And in next series we have the speaker Professor Eva Malmström Johnson will in 9th series and hope you all will participate the next series. Thank you all and keep us motivated, and thank you. And the program is formally ended. Thank you.
Thank you.
Bye-bye, everyone. Thank you.
Thank you so much.
Bye-bye.
Thank you. See you again. Have a nice day. Have a nice evening.